So welcome back everyone after the coffee break to the second session. So we are going to have the discussion on the public data by Jonah Kanner. So Jonah, the stage is all yours.
Okay, that's great. Thank you so much. All right, hello everyone. Nice to see you. So I want to give some introduction to LIGO Virgo Kagra Open Data. Maybe I should say my name is Jonah Kanner. I work at LIGO Laboratory at Caltech, and I also work specifically on the Gravitational Wave Open Science Center. So of course, we're talking about data from these detectors. So we have the two LIGO sites, and then also Virgo and Kagra as well. And data from all of these instruments is collected and made publicly available at the Gravitational Wave Open Science Center. And we have a website which provides a portal to all of these open data. So here's sort of a snapshot of the homepage of the Gravitational Wave Open Science Center. The website does go by the acronym GWOSC, which we say GWOSC, which is a very funny sound, and I'm sorry for that. So here at GWOSC, there's lots of resources, and it's a great place to get started if you're trying to learn about gravitational wave data analysis, including but not limited to this workshop that we're running here today. On the website, you can find the data itself are all available for download. There's documentation, all sorts of notes and text and different ways to try and explain how to work with things. Tutorials, many of which we're going to work through here over the next few days. Software examples and suggested software libraries. Segment lists, very important to say when are times when data are available. And we have some tools to try to make that easier to find. And then also a number of web apps that try to visualize data, make plots, show some basic features of the data. And so in this talk here today, I want to walk through some of these features that are available on the website and also present some introduction to the data itself and how we understand it, think about it, and access it. So to begin, I want to start with this idea of data. So we have these instruments and we're going to say data, 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 but what do we mean? What do we mean by data in this case? And of course, for different instruments, different projects, that word data can mean very different things. So in our case, we're almost always talking about what's called strain data, or I might say gravitational wave strain data. And strain data fundamentally represents stretching or squeezing of the arms of our interferometers. So, strain by the definition of strain is here. It's delta L over L, where L means length. So length refers to the length of one of the interferometer arms. For example, for the case of LIGO, this is a 4-kilometer track where the laser beam bounces back and forth. And so the L here is 4 kilometers. And then delta L refers to the amount of stretching or squeezing of that 4-kilometer track. Of course, as a gravitational wave passes through, the track stretches and then squeezes and then stretches alternatively. And that stretching and squeezing, that's what we record as strain. And here's a sort of filtered picture of strain. And the point I want to make is that this is actually filtered data around the first detection. So this is filtered data around GW 150914. But the point that I want to make is that in the data itself, a peak in the data in one direction refers to, say, a stretching, and then a trough, a bottom, refers to a squeezing. So as the arms are getting longer and shorter, we can see in the data going, let's say, positive for longer and negative for shorter, something like that. So in general, these data are time series data, meaning that each sample has a timestamp. So the x-axis here is time. So over the course of days or months or years, we record data, and each data sample gets a timestamp. And then at each timestamp, we're recording a measurement of the strain, of the stretching or squeezing at that moment. The data spans can span months or years. So we heard in the talk this morning that the instruments run in a series of observing runs. So right currently, we're in our 4th observing run. 04 for observing run number 4, and each observing run can be months, and so we eventually release all of the strain data that spans, the entire set of an observing run. When you're talking about a whole observing run worth of data, it amounts to a few terabytes per year. On the other hand, the first thing to understand our data is that nearly all of our data are noise. So the detections, at least so far, are these transient signals, compact binary coalescence, so mergers of black holes and neutron stars. And these compact binary coalescence, these detections, they're only visible in our detectors for a very short period of time. Each detection could be up to a few seconds, let's say, but in many cases it's less than a second. And so we have months or years of data, but only a handful of seconds worth of signal. So it's really a needle in a haystack problem. The vast majority of our data is all noise. So we have terabytes worth of noise with just tiny bits of signal buried in there at different times. And even worse, to see the signals at all, even at a time when a signal is occurring, it requires an amount of filtering. So the signal, in this case, to see this 150914 signal, this isn't what the data look like as they're recorded on disk. To get to this point requires a number of signal processing steps, which is why we have a whole workshop to teach people, to introduce people to the data, because it's not simple enough. It's not as simple as opening a file and boop, there's the signal, but instead you open a file and what you find is a bunch of noise, and then there's some number of processing steps to be able to find the signal. And so what we're going to do over the next few days is introduce you to the types of processing that you go from a raw data file to be able to actually find a signal. And that'll include some basic signal processing, things like whitening and bandpass filtering. And it can also include match filter searches, which of course are the most sensitive way to search for signals in a large amount of noise. And we'll try to cover all of that here in the next few days. Yes?
In the y-axis, you have already made the normalization.
Yes, that's a great observation. Yeah, that's very important. Thank you for noting that. That's right. This says strain, but that's not really true. This is really, you're right. It should say whitened strain. And so there's been some normalization here. The actual amount of the strain, of course, is very small. The scale of these length changes is something like 1 part in 10 to the 21. But here, this is after filtering. So the units here are arbitrary or normalized in some sense. Yeah, thank you.
So in this L over delta L over L, so we are only observing the space distortion or also time distortion here.
Good question. So again, most of it's noise, right? So it's mostly, let's say small motion of the mirrors or laser noise or all kinds of other noise sources. But in principle, we're trying to measure space distortions primarily. It turns out that the time distortions are second order. It depends on your coordinate system, but in the typical coordinate system, the spatial distortions are first order, and so that's why we think of it as delta L over L. And then the time distortions are second order, meaning they're much, much smaller, so we don't see them.
Oh, okay, thank you.
Very good question, yeah. Okay, and then I'll highlight that we do, with each data release, we do publish a paper that attempts to describe the data release. So if you want just an overview of the data that are available and some introduction to the runs, that's one place to look. Okay, I wanted to give an introduction to our data files. So, what does it mean to open up a data file? What's actually in there? Maybe the first thing to say is that we generally make data available in 2 formats. The 2 file formats are basically equivalent information. We make them available because just for convenience. So GWF is a gravitational wave frame file. This is more or less the standard that's been used by the gravitational wave community for a long time now. So many of the analysis pipelines expect this file format. On the other hand, we also make available an HDF5 format, which is somewhat more popular in other outside of the gravitational wave field, and so in many cases that's convenient. So our data are recorded, it's time domain data, meaning that we're taking a measurement of the strain periodically, and the amount of, how often you record the data is known as the sample rate. So in general, data are recorded with a 16,000 hertz sample rate, 16,384. So 16,000 times per second, there's a data point recorded. And then we also make available downsampled versions of the file, where there's, instead of 16,000 samples per second, there's 4,000 samples per second. And the reason I mention this is that it's important to be aware of the sampling rate when you're working with the data, right? So that sort of sets, it's just one important parameter of what you're doing. Of course, they're time domain data, so each data file has some starting time. We tend to record time using GPS. So GPS here is the Global Positioning System. It's the same time convention that's used for the satellite. So if you're looking at Google Maps or you're getting directions, then you're most likely using this GPS network of satellites, and we use the time convention of that. It's a convenient time convention because it's measured in integer seconds from a starting date. So you have these long 10-digit strings of numbers that tell you the time. And then the bulk of the file is the strain values. So each number, right, the file is ultimately a large collection of numbers. Each number represents a strain sample at one moment in time. And as Lupin pointed out, the scale is quite small. So these numbers, in this example, the scale here is something like 10 to the minus 20 or 10 to the minus 21, because of course this is a very sensitive measurement. And so the scale of the strain measurements are quite small. Just a note on GPS, if you're not familiar with it, it's integer seconds counting from a starting date. The starting date doesn't matter most of the time, but it happens to be a date in 1980. We provide a tool on the website to convert times, so that's at guasc.org/GPS, and you can put in a date and it'll give you the GPS time. Very simple. So I wanted to, so as a way to introduce yourself to the data files and to the strain, we make available a web app. So this is the Quick View web app. The URL is up there. You can find it. If you're on the GWASC website, you can go to the learning path. That's guasc.org/path. And there's links to a few of these web apps. And this web app gives a way to just make plots of some of the data files. So you can go in here and you can put in the name of your favorite event. So here I'll pick the first one, 150914. This is the raw data, and then it's filtered, and you can see the filtered data. There's an audio file, some people like that. And then there's the spectrogram view as well. And so in the spectrogram view, you can see this chirping structure. So sorry, I should use the pointer. You have this chirping structure where as the black holes merge, as they go forward in time, the black holes are getting closer. As they get closer, they go faster. And so you get this boop, this kind of chirp, and you can see that in the spectrogram view. I do want to highlight, I like in this video that you can see here, the first thing that happens is the raw data are plotted. And again, I want to highlight when you open up a data file, you're not seeing the signal. So when you open up and plot the raw data, you're not seeing the signal, you're seeing noise. And that's really important to understand, is that the data are completely dominated by noise. And so going from this step to the line below, there's some filtering applied. The data are, in this case, it's what's called, they're whitened and bandpassed. And I think in some of the tutorials we'll experiment with some of those things and show what that does. And so that goes us, that takes us from a place where the data are dominated by noise to a place where we can, see the signal and study it in the data. All right, so strain data is made available in a number of different ways. These files are available. The most convenient in some sense, or the easiest in some sense, is to go to the website and there's a point-and-click interface. So you can go to the website, click Get Data, and then you click the download button, and then there's And then from there, you pick your data release. So O3B, so O3 again refers to the third observing run. And then you can click the button for the 4 kilohertz data, so that's the downsampled data. And then that'll give you a query interface, and from there you can query from the times you want. But eventually you get to this list of files. And so each line in this table refers to one data file, and you just click the format you want, HDF5 or frame file, and then the file will download onto your computer. So very simple. This is also available, the same interface is available through a Python API. There's a client, so there's the Guasc client that's in pip, so you can do pip install Guasc and you get this little client. And then the client has some commands for retrieving URLs of data, so you can write a little Python script that'll download some data files. Again, very simple. You can also, there's a convenient function, so there's a popular software package, GWPy, and inside of GWPy, there's a command to fetch open data. And so this command will automatically find the data file, download the data file, open it up, and then load the data into an object. So again, very convenient for Python scripting. And then we do have some extended data releases that are not available through the web interface. And so these are available through 2 different interfaces. There's something called NDS2. That's a network streaming service, and then there's the CERN virtual machine file system, which is very convenient if you're working on a large computing cluster. So if you happen to be working on a computing cluster, it's possible, like the Open Science Grid, then it's possible that CVMFS is already loaded up on there, and in that case, that's a very easy way to get the data. And then NDS2 can be interfaced again through the Python client, in this case GWPy. And so that's just a different way to access the data. I did want to mention segment lists. So segments tell us when data are available. So the instruments work in the series of observing runs. They're not observing all the time. And so here's 01 in something like 2015. Here's 02, 03, 04, and 05. And notice, of course, there's big gaps in time between the observing runs. So between observing runs, there's no data publicly available. In general, we're not making astrophysical observations during those times, so there's no data there. So already data are only available during the observing runs. But then even within the observing runs, the instruments can go on and off depending on circumstances at the site. Oh, maybe I should say where we are. So we've got, these 3 observing runs, 01, 02, 03, those data are now publicly available on the Guasc website. The 04 run is in progress right now, so those data are not yet publicly available. They're being recorded as we speak. But then even within an observing run, the instruments go on and off, and data are only available at times when the instruments are in a good state. So we provide this timeline app, guasc.org/timeline, and in the plot here, what you're seeing are times when data are available. So the colored bars, like here's a big, thick color bar. The color bars show times when data are available, and then the white gaps are times when data are not available. And so here's a graphical representation, but of course you can download this as a text file or a JSON so that you've got start and stop time, so you know exactly when you should expect to find data or not. So a bit technical, but very important. You can't find data at times when it's not available. A bit more fun, there are these event catalogs, so you want to know what are the detections that LIGO, Virgo, Cagra have seen. And here an event means a compact object merger, so that's in most cases so far, all cases so far, I should say. That's these mergers of either neutron stars or black holes. They're typically only observable in our data for seconds or less. And there's in 01, 02, and 03, there's, I would say 93, depends how you count, but there's about 93. And of course, there's more being recorded every day now that we're into an observing run. But these 93 detections are what's available so far. And to find these, they're all available through this interface on the website called the Event Portal. And so what you can do is you can click here the transient catalog. This will give you that set of 93 events. Yeah, okay, so there they are. So here's the set of 93 events. They're listed with their parameters. And then you can click each one and you get a detailed view for that event. It includes a spectrogram. So you have this little spectrogram view over here where you can actually, boop, there's the event right there. These links that have file formats, GWF, HDF, each of these is a link to a file download. So through this interface, you can directly download the data, so that's convenient. And also around events, we provide these 32-second files, so you can actually get pretty small files that just contain the data immediately around an event. So that's a fun thing, because you can go in, you can browse, you can see what all the discoveries are, and you can see their physical parameters and compare and contrast. It's a great way to learn about gravitational wave observations. With the event portal, there's also a query form. So if you want to get, say, all the events that have a mass less than 3 solar masses, you can query by mass and get different sets of events that way. And then just these are more snapshots of the event portal. So again, you can find the data immediately around the discoveries. So we do make available a number of different software and tools. This is that quick view app again. But then we also have software libraries, and so guas.org/software. And of course, there's this large LIGO-Virgo-Kagra collaboration. Many people over many years have written a number of software packages that are open source and available. And so you can learn how to find these packages, download them, install them. Many of them are available through pip, so if you want a pip install, that's fine. In general, what we recommend is this Igwin Conda software distribution, and so there's instructions there for how to set that up on your laptop if you're looking for these software packages. I should say some of these packages, in fact, the ones listed here, are ones that we'll be trying out over the next few days as part of this workshop. There's also a number of web apps, like the ones I've been showing. This one was created by a group at Cardiff that makes a nice scatter plot of the events, but just in general, from the GWASC website, you can find a number of apps for plotting and visualizing data, quite handy. Whoops. And maybe the most important part, what do you do if you're stuck? And so we have a discussion forum. The discussion forum is available at ask.igwin.org. It is a public discussion forum, so anyone can create an account and post a message. We do, I mean, it's a best effort basis, but we do have a number of people who try to monitor the board and provide answers. Also, because it is a public discussion forum, you're welcome to provide answers, which is wonderful and very helpful. And we are recommending use of this for the workshop. So as you're working through the tutorials over the next few days or the data challenge, if you get stuck, if there's a bug, if you have questions, if something's not working, please do post it, and then that'll give us an opportunity to fix what's broken or give you some hints. So please do use that. Okay, so that's the end from me. I just want to highlight that we've got this website, guas.org. We've tried to put a lot of resources there. You can download data, you can learn about data, you can find segment lists, you can browse catalogs, events, and also a lot more. So thank you so much. I really appreciate your time and attention.
Thank you, Jonah, for that wonderful discussion and pointing us to the right resources. So time for Q&A. So any questions from on-site? Okay.
What's the advantage of using the GWF file format?
Yeah, that's a good question. So the advantage is that many of our software packages expect it. So there's a great deal of analysis software that's open source. And in general, most of those packages expect the GWF format. So some of the packages have been now that we've been making, recently, right? I mean, recently in the last 5 to 10 years, we've been making available data in HDF5 formats as well. But in general, the internal work, the collaboration work is done using the GWF format. So in general, many of the software packages expect GWF. So in general, if you're using software written by members of the LIGO-Virgo-Kagra collaboration, probably expects GWF. If you don't want to use that software, if you want to, use Python packages off the shelf, it might be more convenient. Something like Pandas, for example, can read in HDF5 more naturally. So it just depends what software you're using.
So it's just a choice of my own preference.
Yeah, it's convenience.
Yeah, that's great.
Yeah,
Okay.
for sure. Yeah, in the public archive, the content is essentially identical. So it's really to provide a convenient interface to whatever software you might be using.
Okay, that's great. Okay.
Also, a quick question also recurring to the formats. Since you mentioned that there are two formats, so which one do you recommend to use, or do you have any plan to unify the formats?
Yeah.
Any consensus on that?
Yeah, so again, in terms of format, it really just depends on the software you're using. Much of what we're going to do over the next few days will be using GWPy as an interface, and GWPy will read either. So you can actually use either file format in that case. But I'd say as a good rule of thumb, if you're using LIGO, Virgo, Kagra collaboration software, probably better off with the GWF file format. If you're using software from literally anywhere else, then you're better off with HDF5, right? Because so quote unquote standard packages or common packages, things like Pandas, things like NumPy, I don't know, MATLAB, right? These things don't know about GWF. GWF is specialized to our field. So if you're using the specialized software, it's probably going to expect the GWF format. If you're using off-the-shelf tools from data science, from machine learning, et cetera, you're probably going to be better off with the HDF5. But again, the content's the same. So if you can make it work, then great, right?
Is all data contains two formats? Or only?
Yeah, so good question. So we make these different interfaces that we make available, the point and click, the Python client, and the direct load with GWPy. All three of those are interfacing the same web-based data archive that's available at guas.org. And all three of those, in those cases, yes, they all contain, the data is available in both formats. The exception is this extended release. So for example, the extended release includes things like auxiliary channels. So I said that, I opened this talk by talking about strain data, but what if you don't want strain data, right? What if you want data from a seismometer that's at the site? Or what if you want to know the power levels at the site? Sometimes people ask for that. So we've started making these so-called auxiliary channels available in this extended release. And there, we're doing less processing. We're just giving people basically what we use internally. And so we're making it available only in GWF. So this extended release on NDS2 and CVMFS, those are only available. That's the one exception. That's what's only available in one format.
Thanks.
Okay, so do we have any on-site questions? Oh, okay.
Thank you very much for your talk. I had a small question at the beginning with regard to the strain, the definition of strain. You presented that as the length difference over the original length. Because the fact that you have two arms, how is it like dealt, or do we have any information on like which kind of deformation we are talking with, or is it like any kind of directionality of deformation doesn't really matter?
Yeah, great question. So the delta L is, in principle, the delta L is the difference between the X arm and the Y arm. So I don't know, I'll get the sign wrong, but it's either the X arm minus the Y arm or the Y arm minus the X arm. So that's what, right? Remember, it's the whole instrument, the whole measurement concept is based on this difference in path lengths, right? The whole concept of interferometry is looking for differences between the X arm and the Y arm. So the measurement is really, let's say, the X distance minus the Y distance. So the sign of it the sign, if it's positive or negative, tells you, I'm going to use the pointer for the benefit of people online. The sign of it tells you, is this arm shorter or is this arm longer, right? So if it's, positive or negative. But that's it. That's the information we get. There's no rotation. I'm not sure if you were suggesting that. But it's either one arm is longer or the other arm is longer. Does that make sense?
Okay. Thank you.
Okay, thanks. I think we have one question online about so there's a question like, all the packages and software are available for Windows?
Yeah, so in general, the answer is no. Most of the software is written assuming sort of a Linux kernel. So most of it will work either with Linux computers or with Mac computers. In general, much of it will not work for Windows. There are exceptions. There are some packages that work for Windows. I believe, so one of the packages we're going to highlight in this workshop is GWPy. I think GWPy will work on a Windows machine. But in general, our recommendation is to use either Linux or Mac. Because of that, because we understand that many people use Windows machines, that's the reason that for the purposes of the workshop, we're using these online notebooks. So for the workshop, we're going to do things either in Google Colab or in MyBinder. Both of work in the web browser, and so they're not actually doing the computing on your computer, they're doing the computing in a remote server. And so in that case, it doesn't matter what kind of machine you have. You can have Apple, Windows, you can do it on your phone, you can do it on a tablet, it doesn't matter. But if you want to install the software on your computer, in general, it's going to work better if it's either a Mac or a Linux. And if you'd like to do that on a Windows machine, in general, you need to look at something like a virtual machine or a Docker container or a dual boot. So there are certainly options for making the software run on Windows. But in general, you want to, in fact, I think modern Windows machines, I believe there's actually like a Linux app of some kind.
I think Windows 10 and 11 might be helpful in running this one.
Yeah. So in general, you want to look to see how can you run Linux software on a Windows machine, and there are options for doing that. But you'll have to jump through some hoops.
Okay, that's great. So we are about the hour, so let's thank Jonah for this wonderful discussion. Okay.
Thank you very much.
So we have the next talk by Takahiro Yamamoto, and he's going to speak on the continuous wave. So let's welcome the speaker.
Okay, so good morning. I'm Takahiro Yamamoto from University of Tokyo, Japan. I'm going to introduce about the continuous gravitational waves, and I think that this is the first time to introduce various types of gravitational waves, not only except other than the compact binary coalescence. And I'm really happy, and I would like to thank to organizer for giving us the chance to introduce this exciting source of gravitational waves. Okay, so let's start from the introduction of the continuous waves. So far, LIGO, Virgo, Kagra collaboration detects many gravitational wave events, and they are all coming from the compact binary coalescences, but theoretically, we expect the various types of gravitational waves. And so here's a table of the classification of the gravitational waves. In terms of duration is short or long, and the waveform is well modeled or unmodeled. And yeah, so in day 2 or day 3, we have a lecture about the burst type and the stochastic type, these two lower panel. And in this talk, in my talk, I will study about the continuous waves, which has a very long duration, and the waveform is very well modeled. So here's several sources of continuous gravitational waves for the ground-based detectors. So most people expect that a neutron star is most likely sources of continuous gravitational waves, because we already know that there are many lot of pulsars in our galaxies by radio telescope observation. They detected as pulsars, which the event of the many radio pulse train with a very accurate period, a very stable period. And that was coming from fast rotating neutron stars. And if these neutron stars have a small distortion, it will emit gravitational waves. And this gravitational wave will be observed as continuous like gravitational waves in the ground-based detectors, and it will give us information about the astrophysics of pulsars, and also the information about nuclear physics, that controlling the inner structure of the neutron stars. And recently, people discuss about some other exotic type of sources. In the middle panel, here's a schematic picture of the boson cloud around rotating black holes. So if there are some ultralight bosons, and they will extract the energy from the black holes, and they form some condensation, and it will emit a gravitational wave by pair annihilation or something, and it will be detected by other continuous waves. And yeah, so if we detect such a gravitational wave from boson cloud, it's nothing but the discovery of the ultralight bosons, so it will give very huge impact to the particle physics. And in the right panel, I show some artist images of the binary black holes. The black hole consider that they will be formed in the astrophysical scenario. I mean, the very high mass stars at the end shrinks, and they will become to the black hole. But in theory, there is another possible scenario to form the black hole. It is a cosmological origin, the so-called the black holes having a cosmological origin is called the primordial black holes. And unique feature of the primordial black hole is that it can have a very wide range of the masses from the 10 to 15 kilogram to the like a supermassive black hole or something. And particularly is the planetary mass primordial black hole formed binaries, then if we the gravitational wave from this system can be detected as a continuous waves in the ground-based detectors. So this discovery must have an impact to the cosmology. So in summary, detecting the continuous gravitational waves will give impact to not only the astrophysics, but also nuclear physics, elementary particle physics, and also cosmology. So this is why we want to detect the continuous waves. And yeah, here's a list of the character of the continuous gravitational waves. It is a persistent, long duration, and quasi monochromatic signals. It means a very stable frequency, but with a slight frequency change rate. And the amplitude is quite small. Amplitude is very weak. For example, the spinning distorted neutron star, we put typical value as a parameters like ellipticity, how distort the, how large the distortion of the neutron star, and here pulse period, it means nothing but the rotating period of the neutron star and the distance to the neutron star. Then in theoretical, we get amplitude of 10 to minus 26. It's so, for example, the binary black hole, GW 150914, amplitude is 10 to order 10 to minus 21 at maximum. So compared to that, you can find the continuous wave, amplitude of continuous wave is quite small. To detect such a very big signal, we need to use a order year long strain data and accumulate them. And so far, we have not detected continuous waves yet. And so instead of the discovery of continuous waves, we have a constraint on the amplitude of continuous waves. This figure shows a constraint on amplitude obtained by the all-sky search. We don't assume any sources, and we search over entire sky, and we get amplitude constraint as a function of the frequency. And so it's at from 60 hertz to 500 hertz, the constraint is order 10 to minus 25 or something. Okay, so let's look at the waveform model in detail. This is a waveform model in source frame. When the source emits continuous waves, the waveform is quite simple. And here I use tau as the time coordinate. It describes the time when wavefront reaches at the solar system barycenter. And we have the gravitational wave will have two polarization, plus mode and cross mode. It will be described by the cosine and sine function. And the phase can be described by like this. It looks a bit complicated, but it's nothing but Taylor expansion of the phase. And here's so the important parameter is Fk. Fk is a case derivative of the frequency by time, with respect to time. So usually in most search, we include only F0 constant term and F1, and at maximum F2. Okay. So at the emission, the model of continuous wave is much simpler than the CBCs, but detector motion makes it very complicated. So let's move to the next slide. We have a very complicated waveform model of the continuous waves in detector frame. So we need to include three effects: inclination angle and detectors antenna patterns. They are geometrical configuration relative to the source. And the third one is Doppler modulation due to the detector motion. The Earth rotating and Earth orbiting around the sun, so it will make a Doppler modulation in the frequency. And it can describe as the changing the type coordinate from the source frame to the detector frame. Yeah. Here, the RT is the detector location with respect to solar system barycenter, and the N is a unit vector pointing to the source. So finally, we get the waveform model of the continuous waves, which we will detect. So these first two factors will introduce the modulation in amplitude. But the last factor will introduce modulation in frequency, and gravitational wave search with well-modeled waveform requires a very accurate modeling in frequency. So let's look at frequency modulation in detail. So, so based on the previous slide, we can have a frequency modulation, and this is a rough estimation of the frequency which we will observe. And the right panel shows frequency evolution in time, and from top, we plot frequency evolution in order 1 days, and you see the oscillation in time, and this is this corresponds to the Earth's daily rotation. And zooming out, we plot frequency in order 100 days, or order 1 year, and you see again the oscillation in frequency, and this is this corresponds to the annual oscillation, which corresponds to the Earth's orbital rotation around the Earth. And again, zooming out, move to looking at the bottom panel, we see the order 1,000 days of frequency evolution. We see that this year annual oscillation, and the trend that frequency gradually decreasing. This is intrinsic evolution, like for example, the pulsar have a period gradually decreasing, and it corresponds to that, to this trend. So to detect the continuous gravitational wave, we need to resolve such a hierarchical frequency evolution characters. Okay, so here's two main difficulties in continuous gravitational wave searches. First one is non-Gaussian detector noise. So, the gravitational wave detector have many noise sources, and the most component coming from has a Gaussian character, but there are two types of non-Gaussian detector noise, so-called glitches and lines. They can affect the sensitivity of search by increasing the false alarm rate and elevating the noise powers. And second difficulty is computational cost. So as I said, we need to accumulate very long strain data to detect continuous waves. So we need, so continuous wave searches are quite, sensitive to the small difference in signal parameters, and it will cause a heavy computational cost. So, okay, so let's look at more detailed glitch. This panel shows a list of glitches, various types of glitches, and yeah, so it is burst-like disturbances, and each panel shows spectrogram, but in the spectrogram, the time duration is about less than 1 second. So for the CBC search, the glitch cause a big impact. I mean, the glitches can mimic the signal from compact binary coalescence, but for continuous waves, glitches cannot be the sources of confusion with continuous waves because signal character is quite different. But it can affect the estimation of the noise power spectral density by increasing the noise floor. And second type of non-Gaussian noise is instrumental lines, and it is narrow band persistent artifacts. And here I plot amplitude spectral density taken from O3A observation of the LIGO twins, and you see that this U-shaped noise plus very sharp line, very sharp peak, and they are all instrumental lines. And yeah, there are several sources. Yeah, some lines. For some lines, the sources are identified. For example, the 60 Hz power line or violin modes of suspension or something. And but for some of them, we don't know the sources. You know, the instrumental lines are narrow band and persistent, so it shares a common feature to the continuous wave, so it can mimic the continuous wave signal, so it will increase the false alarm rate. So this is a difficulty in continuous wave search. So in this lecture, I will not go more detail. I will not go more detail about the non-Gaussianities. So second difficulty in continuous wave search is that computational cost. So here, let's briefly look at how large the computational cost, particularly the dependence on the observational period. So idea is that the idea is that how fine do we need the resolution for the parameters? So we estimate the difference in frequency, and it should be smaller than the inverse of T observation. It's a natural resolution in frequency. Okay, so we have, so let's remind that waveform model we have here. We have the waveform has parameters fk, and usually we include only f0 and f1. And also we need assuming if we do not assume any target sources, then we need to search over the whole sky. So the sky position is also the parameters. Okay, and so we consider the resolution in frequency parameter f0, f1, and the sky position. Okay, resolution in f0 is nothing but the frequency resolution, so it naturally is the inverse of T observation. And f1, frequency change rate, should be the inverse of square T observation. So because that So frequency change because of the difference in F1 should be the delta F1 times T observation. Okay, so and delta F1 times T observation should be smaller than T observation inverse. So we get this. And again, and also we estimate the resolution on the sky, and this is coming from the Doppler modulation. And I skipped the detail, but anyway, these angle resolution should be scaled as a T observation inverse again. And so you need so each grid point in the parameter space should cover the certain volume in the parameter space, but it scales as a T observation to -5. You know, this coming from the multiplying all these resolutions. And the computational cost should be scaled the number of grids times computational cost per grid. So computational cost per grid should be scaled again the T observation typically. So it gives you the computational cost scales T observation to 6. It's quite so steep dependency. So long observation time leads to the rapid increase in the computational cost. So this is a second point of the difficulty in continuous wave search. So we take another. So in this estimation, we assume that we treat whole observational data at once, but usually we take different approaches like so-called semi-coherent search. So in this search, we divide the strain data into very short segments and process each segment coherently, and after that integrate them. So typically we use coherent length of 30 minutes or something, but it can be longer. But anyway, it's much shorter than the whole observational period. Of course, the sensitivity is degraded compared to the full coherence searches. So because we lose the coherence between segments. So, but under the limitation of the computational resource, semi-coherent searches can show better sensitivity than the full coherent searches. And So so far many semi-coherent algorithms are proposed, and each algorithm returns the candidates which satisfies the criteria, and they will be followed by the follow-up search to confirm whether these candidates are astrophysical signal or detect artifacts or something. Okay. And this is some list of the various types of continuous wave search. And the horizontal axis shows the computational cost, and the vertical axis shows the sensitivity. And from the top left, targeted searches in which we assume that we know that frequency parameter, F0, F1, and so on, and also we know the source location. So this is applicable for the search gravitational wave from non-pulsar. So, and narrowband searches. In narrowband searches, we only know the F0 and location, but we don't know the frequency change rate. And here, directed searches, we assume only the location is known, such as supernovae remnant or something. And right bottom, there is blind searches, or in other words, all sky searches. We do not assume any sources. We search over all parameter space, frequency change rate, and all sky. So message is that the more knowledge we have, the better sensitivity, as the more efficient the search is. So, and blind search, all sky search, the most expensive task in gravitational wave astronomy. And yeah, in this talk, we focus only on all sky search to cover the not only pulsar, but also the interesting exotic sources. So these are the list of search pipelines employed in all three all sky searches. Here's the time domain statistic, frequency half, sky half, power flux, and SOAP CNN. And yeah, we provide you with hands-on tutorials for the F statistic and the frequency half. So I will explain them. Okay. I will have a drink.
Any questions for the moment?
I have several questions. The first one is that you mentioned that three possible origins are related to the continuous wave. But in most of your talk, you just talk about continuously spinning pulsar. Yeah, even for the spinning pulsar, the signal to noise ratio is still very low. So if we can really detect a continuous wave, so which one of those three origins can be the most possibly detected?
You mean that identification the source after detecting?
Yeah, which one can be the most probably be detected?
Most probably.
Or you say, I mean, both of those signal to noise ratio are very low, so they cannot be easily compared. So we don't have any answer yet.
Yeah. Okay. In my opinion, that we know that the pulsars should be the
most easy
primary source, because we know, yeah, for some of neutrons, we have let's say you know, we have a few thousands of pulsars already detected by the radio astronomy. So we know the information about the neutron star.
Okay.
Right? So we use the information from the radio astronomers to search the continuous wave. So, and yeah, so, and another point is that current sensitivity is, yeah, there is some reference amplitude, so-called spin down limit. It can be derived from the energy loss, equating energy loss by gravitational waves and energy loss of loss of rotating energy. It can be estimated from the pulse period and time derivative of period.
Okay.
So, yeah, current sensitivity is for targeted search. Current sensitivity breaks this spin down limit. So, yeah. So,
yeah. My second question is related to what you just replied to me. I just want to know, you mentioned that we also need to count for the frequency change. But we know that the pulsar can spin down. So when you count for the frequency change, did you also consider the spin down of the pulsar inside it? Or we need to have additional term to count for the spin down of the pulsar?
So what do you mean? The spin down is
yeah.
Spin down. Observing the spin down is essential to confirm the source.
Yeah,
yes.
but when you mention the computational cost of to search for the continuous wave, the frequency change is one important issue. So I just want to know when you mention a frequency change, where the spin down of the pulsar, such kind of effect has already been included inside the frequency
Pipeline.
change.
Yeah. So all these pipeline include to first derivative of f.
Oh, I see.
Yeah, and the range is depending on the pipeline, but typically from it's up to 10 to minus 9 hertz per second or something.
Okay. So my third question is that you mentioned that some noise might be effect on the search of the continuous wave. For example, the glitch and the lie. I think all of these are related to the instrument. But here I want to ask the real glitch of the pulsar. It means that the pulsar may suddenly or immediately change its spin period. Well, it also affected the detection on the continuous wave. Or it may not affect. We still can detect a continuous wave, but maybe we can also find a sudden jump in the frequency like that. I don't know.
Yeah, it will affect much. I mean, so for example, if we want to search for unknown neutron stars, then such a
So it means that for your target search, you usually would like to select the pulsar with many glitches. It means their timing solution is always stable, right? If you want to select the specific target to search for a continuous wave.
do you mean that people in continuous wave consider such a glitch or a pulsar glitch or something?
Yeah. I mean because it will effect on the search of the continuous wave. So maybe we just don't want to search those pulsar have many glitches. Yeah, if we want to.
Sorry to interrupt. I think we are running the hour. Can we take the discussion later on? Yeah, okay. And no, it's a problem, not a problem. So, and we have got like 3 questions online.
Okay.
So, would you like to answer them?
Yeah.
Yeah. So, yeah, the first question that comes is, you might have shown equation for a spinning neutron star, and the participant is asking to show the derivation of that. I mean, maybe share some documents later on.
How this equation for spinning neutron is derived is this one, maybe this slide or something. Yeah, so it shares the material for this. Okay, I will put. Yeah, so in the latest, in the last of this slide, I show the references for the review article or something. You may find the derivation or
Okay.
so
That would be great. So we have another 2 questions. So so could black hole X-ray binary systems be the potential candidate for detecting continuous gravitational waves?
Yes, exactly. So, yes. So actually, we search continuous waves from signals X1, X-ray binary, and at that, not black hole X-ray binary, but at that time we assumed that central source should be a neutron star. But anyway, we have such a X-ray binary as a target. And difficulty, additional difficulty coming from the binary motion of the source. You know, it will introduce the frequency modulation to the waveform. So it will enhance it will increase the computational cost again.
Okay, so I guess there's a follow-up questions on that. So when we detect the continuous gravitational waves, how efficiently would they be classified depending upon their origins? Let me repeat it for the on-site participants. So when we detect continuous gravitational waves, how efficiently would they be classified depending upon their origins?
I think this is related to these three sources, maybe. Classification of these three sources.
Yeah,
maybe.
yeah.
And so first one, and neutron stars and primordial black hole binary could be easily distinguished because the pulsar should have a negative frequency change rate, I mean the spin down, but for the primordial black hole binaries should have increase in the frequency, so positive value for spin change rate. So so frequency change rate is can be used for the discrimination of the source.
Okay, that's great. So I think we are almost about the hour. Sorry. So do you have more?
So I should introduce the two methods.
Okay. So
How should I that?
should we? So this is related to the hands-on session. These introductions are related to the hands-on session.
I will introduce what's going on in this method F statistic and how to transform.
So do we continue or no? Okay. So how about like you have a hands-on session in the afternoon after lunch?
Before hands-on session.
Yeah,
I will
before.
continue.
Yeah. So you want to do this before hands-on session?
Yeah.
Okay. Maybe if you can make it very quick.
Make it
Make
quick before.
I mean, you can do it right now, but can you be a little quicker?
Okay.
Yeah.
I
Okay.
will try.
Thank you. Yeah.
Okay, so let's move to the explanation about these two a method. So F statistic is based on the technique so-called match filtering. It is a well-known technique when we know where we have we have models for gravitational waves. So here's a notation: S is strain data, and H is a predicted gravitational wave waveform, and N is detector noise. And in this match filter, actually it is based on the likelihood ratio statistics, and we can estimate the likelihood of strain data in two cases: the absence of signal and the presence of signal. And so the detail, this definition is written here. And anyway, we can estimate the log likelihood ratio, something like this. And so here we rewrite the signal model. The point is that we have many parameters to be searched. So for F0, F1, and so on, and alpha and delta sky position of the source, and amplitude of the gravitational wave, and inclination angle, polarization angle, initial phase. So here's 7 plus S parameters. Yeah, so typically 7 or 8 or 9 parameters. Searching over such many parameters are too heavy to carry out. So, but we can rewrite the signal model in this form as a linear function, linear combination of 4 H's, H1, H2, H3, and H4. And these H have time dependency and depends only on F0 and F1, F2, and alpha and delta. So they control the frequency evolution. And the coefficients, we denote the coefficients by A mu, A1, A2, A3, and A4. And they are time independent, and also they only include only these 4 parameters. It controls the amplitude. So point is that we can separate these 8 or 9 parameters into this way. So we can rewrite the likelihood ratio into this. And this is a quadrature of A in A. So we can easily maximize over the amplitude parameters and maximize over amplitude parameter analytically. So this is a definition of F statistic, maximized log likelihood maximized over amplitude parameter. Again, so this F statistic depends only on the frequency parameter, I mean F0, F1, and or source position. So using this technique, we can reduce the dimension of the parameter space by 4. Okay, and I will skip the statistic of F, and yeah, so in this F statistic technique, after maximize over A mu, we need to do is that calculate the F statistic for each grid point in this reduced parameter space. Okay, so yeah, this is a first technique, first method for the continuous wave search. Second one is frequency half, and start point of this technique is that making peak map from periodogram of the strain data. So here I show that power of the Fourier transform of the first only one SFT segment, and here I plot here the threshold, and we pick up the local maxima and the values exceeding this threshold as a peak, and we put we see the many peaks in these time frequency plot. So this is a start point. And in half transform, we assume the relation between the peak map and the parameter space. So half transform will convert each point in peak map into several set of points in parameter space. So if the point of peak map is point in parameter space is consistent to a peak in peak map, then the value will be incremented by 1. So, and carrying out for all these, each peaks in this peak map, we get the statistics in the parameter space. So this is a demonstration of the Fourier-Tarbaz continuous wave, but this is a demonstration for half transform. And yeah, here we have a data set of X and Y, and they have a relation as a linear function plus noise. And we want to estimate the coefficient A and constant B. And if we for each values, we increment the value in the parameter space if they are consistent with parameters. So as the number of data increase, you gradually see that you will find true parameter value of A equal 1 and B equal 0.5. Okay, so such a kind of transformation analysis we carried out to the peak map. And before the carrying out this transformation, okay. Before carrying out this transformation, we need to correct the Doppler modulation. And yeah, so we carry out this Doppler correction for each grid on the sky. So we assume if we pick up the correct source position, and then after Doppler correction, we will have a straight line in the time frequency domain. Because in this in this plot, we just assume that signal has a F0 and F1. Okay. So after correcting the Doppler modulation, we get this kind of frequency evolution, just a linear, and we can translate it into the relation between the F0 and F1. And again, this must be the straight line in the F0 and F1 plane. And using this relation, we count the number of the peaks consistent with each grid points in the parameters. Okay. So in the hands-on session, we will carry out F statistic search and search by this half transform. Okay, so this is a summary. So continuous waves will provide us very fruitful information about astrophysics, particle physics, and cosmology. But the searches of continuous waves challenging due to the computational cost and the existence of non-Gaussian noise. And various semi-coherent searches are employed to detect continuous waves. And we will carry on the hands-on for the F statistic and half transform. So in this talk, I didn't mention about these following topics. I will skip it. And here's several references. These are 5 recent review articles. And here's tutorials and slides. And the hands-on session, the tutorials taken from examples in PyFstat, and tutorials on frequency half made by Andrew Miller. So, okay, that's all.
Okay.
Sorry for taking time.
Okay, let's thank the speaker. Thank you, Yamamoto-san, for your wonderful